Chapter 1, Part 3, Chemical Bonding, Electronegativity, and Identifying Polar and Nonpolar Molecules. There are two main types of chemical bonds. The first type is the ionic bond, also called an electrostatic bond. Bonds, and this is used in quotations because bond is being used kind of loosely here, are formed by the transfer of one or more electrons from one atom to another to create ions. In other words, a redox reaction. This is an attractive force between oppositely charged ions. So this is different from our second type, which is the covalent bond, where electrons are actually shared between atoms. So the first type with the ionic bonds, you have something that's really more of an attraction, and a covalent bond is more of like a shared thread between the atoms. They're actually being held together. All bonding uses valence electrons. That's why we spent time in the last part of this discussing what valence electrons are and how to identify them. All elements except for teeny tiny hydrogen and helium want to have 8 valence electrons. This is known as the octet rule. Boron also often falls in that exception. Atoms will make bonds or undergo redox reactions in order to achieve the octet rule. You may be wondering what's special about 8 valence electrons. If you think back to our electron configurations, having 8 valence electrons means that your p orbital and all 3 of your p orbitals and your s orbital are full. So your entire outer shell, your valence shell, is completely full. This is a stabilizing force to have all of those electrons present. Electronegativity is the measure of the ability of an atom to attract electrons. In simpler terms, this is a way of saying electrons like to spend more time on certain atoms than they do on others. Electronegativity as a periodic trend increases from left to right and up the periodic table. So if you're looking at the periodic table, fluorine is going to be your most electronegative element. You'll notice that we're not really including the noble gases in this trend. Atoms with higher electronegativity, typically nonmetals, are more likely to gain electrons through covalent bonding or reduction. For example, here we have chlorine gas. We can balance this equation by plugging a 2 in here. In the chlorine gas, each of these chlorine atoms only has 7 electrons. Hopefully you recall that each covalent bond is made up of 2 electrons. So chlorine, each of these atoms here, has 7 electrons. And that's also how many electrons each chlorine would have come into this molecule with. If you take a look at the periodic table, you'll notice that chlorine is in the 7th group, meaning that it has 7 valence electrons. Now, because it has 7 electrons, and it would really like to have 8 to fulfill that octet rule, chlorine is very easily reduced. So it is very easy for chlorine to gain electrons and become chloride. Chloride has 8 electrons around it and has a complete octet. Another example here showing differences of electronegativity is this water molecule. In this image, we're showing that there is a dipole in this molecule by using dipole arrows. Dipole arrows show that electrons are focusing more on one atom than the other. And that's kind of a weird thing to say. It's not like electrons have, feelings and make choices and things like that. But keeping in mind that we have these covalent electrons and we have covalent bonds, and we have a shared electron cloud between the oxygens and the hydrogens within the water molecule. These electrons are more likely to be found on the oxygen atom because the oxygen atom is much more electronegative than either of the hydrogens. So oxygen is going to have a greater electron density than either of the hydrogen atoms. One way that we can show that is to use these dipole arrows. Another way that we can show that is to indicate that oxygen has a partial negative charge. Now notice that this is not a full negative charge. We're not assigning a formal charge of negative to the oxygen. We are saying that there is a partial negative because the electrons are spending more time on the oxygen than they are on the hydrogens. And similarly, the hydrogens have partial positive charges. So water is going to have this pretty intense dipole across it as a molecule. Atoms that have lower electronegativity, such as metals, especially those in group 1 and 2, are more likely to lose electrons through oxidation. So taking a look at this balanced equation of sodium metal and chlorine gas, sodium is found in the first group in the first column of the periodic table. Sodium has one valence electron. In order for sodium to have a full octet, it's going to be a lot easier for sodium to lose that valence electron and only have the full valence shell in its lower level than for it to suddenly gain 7 electrons, right? So sodium would prefer to lose one in order to have a full octet, even though it looks like it has 0 here. And then we've already talked about chlorine, but again, it's starting off at 7 here, and the chlorine atoms end up with 8 here. So each of these atoms are now much happier because they have a full octet. We've also created an ionic compound. We have sodium chloride here. So there's going to be an electrostatic attraction between the positive charge on the sodium and the negative charge on the chlorine. This slide is just a little animation showing the trend of electronegativity. So cesium is our least electronegative atom on the periodic table, and this arrow is pointing towards fluorine. Fluorine is our most electronegative atom on the periodic table. Moving on to polar bonds and molecules. We just talked about dipoles, looking at the water molecule. Now we need to discuss when is a molecule itself polar. So a bond is polar when there is a difference in electronegativity of the atoms involved in the bond. We saw this in the water molecule example. A molecule is polar if it has polar bonds and the vector sum of its bond dipoles is non-zero. That's a pretty serious mouthful of words there. We're going to do some examples in case that's not making a lot of sense. A molecule is nonpolar if it has all nonpolar bonds, or it has polar bonds and the vector sum of its bond dipoles is 0. This is something that occurs when there is symmetry in the molecular geometry. So we're going to look at some examples here of covalent bonds that are either polar or nonpolar. We're going to figure it out together. So looking at the periodic table, you'll notice that hydrogen is all the way on the left, chlorine is all the way on the right. There's going to be a pretty significant difference in electronegativity. So there is very likely to be a dipole along this molecule where the electron density lives mainly on the chlorine, not so much on the hydrogen. Because of this, this molecule is polar. You can see that it has two opposite poles that have different charges essentially. You can kind of look at this like a battery, right? A battery has a positive side and a negative side. A battery is polar. If a molecule kind of resembles a battery in that way, then it is going to be polar. We already talked about water, but since we're talking about polar molecules, I want to discuss this a little further. So it's really, really important to consider the molecular geometry of a molecule. I'm going to draw water out in two different ways. So we already have it drawn with the correct bent geometry, but what if I had drawn water linear? So looking at our top molecule, which is the correct structure, we've already talked about how we have these dipoles showing that the electron density lives on the oxygen and the hydrogens are going to be partially positive. This creates two different sides of the water molecule. You can draw a line clearly separating the negative end from the positive end, right? So this resembles a battery in that way, and this molecule is polar. But what if I did not take into account the geometry of the molecule? In this example, I've drawn water linear, which is not correct. Please don't do that. I would still have a partial negative on my oxygen. I would still have partial positives on my hydrogen. But now I actually have 3 regions of charges, right? There's no way for me to draw a line through this and say, oh, I have my positive on one side and I have my negative on the other. Instead, what I have is positive on the left, negative in the middle, and positive on the right. This is 3 different regions. This does not resemble a battery. This would be an example of a nonpolar molecule, if this were the correct structure of water, which it 100% is not. And then in this example, ammonia, this is another one where taking into account the molecular geometry is so important. A lot of students may be tempted to draw ammonia like this, with the hydrogens equally spaced around the nitrogen, maybe even forgetting that that lone pair exists at all. And we'll look at why that would be a problem later. Nitrogen and hydrogen have differences in electronegativity. So we would see a negative on the nitrogen, positives on each of these hydrogens. This is going to give us a negative region and a positive region. In this molecule, we can see very clearly that there is a lack of symmetry in this molecule. We have our most electronegative element up here, which is fluorine. And then we have carbon and hydrogens. These are all going to be significantly less polar than fluorine. So this whole area is going to be kind of positive. So we are able to draw a line through this molecule. We have a negative portion on top, a positive portion on the bottom. The dipole for this molecule goes kind of straight up. You can also look at it this way, but that's a little messier, a little bit more going on. And there's an overall dipole for ammonia as well. I just didn't draw it there. Now looking at our non-polar examples, I have a molecule that looks a lot like the one that we just did. This is just methane. There are no electronegative atoms on here. There's a very slight difference in electronegativity between hydrogen and carbon. So if you really wanted to, you could consider that it's possible that there's more electron density on the carbon. But what you'll notice is that even if you do want to consider that, this is a situation where the vector sum of the bond dipoles is 0. All of these dipoles are pointing in towards the middle. So you would have this kind of spherical surface that would be partially positive, and you'd have a partially negative center. There is no pulling in opposite directions. This is an example up here of a bond dipole that the vector sum is non-zero, right? There's a clear difference between positive and negative. In this molecule, there is no difference there. And that is a factor of the molecular geometry here, the fact that it's tetrahedral. In our next molecule, we see something that looks a lot like that bad example of water that I drew. We have a difference in electronegativity between carbon and oxygen. The oxygens are going to be significantly more electronegative than the carbon. So you're going to have a big old partial positive on the carbon and big old partial negatives on the oxygens. However, we end up with 3 distinct regions of charge here. So you can either look at it as, I don't have those 2 distinct regions, or you could say I have these 2 dipoles and they're pulling in exactly opposite directions, right? So there is no overall dipole. If 2 people who are equally strong are pulling on the same rope in opposite directions, then you would never ever see the end of that game of tug of war. In a situation where the vector sum of the bond dipoles is non-zero, there is a winner in the tug of war.